Hello, welcome everyone. In today's lecture, we are going to look at forced vibration of a single degree of freedom system. So in the previous lecture, we looked at the free vibration of a single degree of freedom system, which essentially means that the system is not continuously forced. Essentially, the forcing function is zero. You provide an initial velocity or initial displacement and then let the system vibrate by itself. We are not applying any continuous force. In today's lecture, we are going to look at a case where we're constantly applying a force to the system. This force is going to be a time-varying force, and it can take many different forms, but we will focus only on forces that vary sinusoidally with respect to time. So essentially, it's some F or P naught times cos omega t or sin omega t or something like that, okay? So by the end of this lecture, you will be able to analyze the forced vibration of a single degree of freedom system, which essentially means that you will be able to compute what is the displacement x as a function of t for a forced vibration system, okay? So now let's start looking at the forced vibration of a single degree of freedom system, okay? So again, if you recall, the governing equation for a system like this is mx double dot plus, cx dot plus kx equal to f of t, okay? And again, to recall, essentially you have a system where you have a spring, you have a damper, and that is connected to a mass, and the force F is applied to that mass. Okay, so this is the spring K, and that's the damper C. Okay, that is where we get this equation mx double dot plus cx dot plus kx equal to f of t, where x dot is essentially the derivative with respect to time. Okay, now in this case, we are going to assume a very specific form of the forcing function f of t, which is p naught sine omega bar t. Okay, again, this is not the only possible forcing function, but in many engineering systems, you will find that the forcing function f of t is either some f naught sine omega bar t or some p naught times cos omega bar t, or a combination of sines and cosine. So it will be sine omega bar t times some constant c1 plus some sine cos omega bar t times some constant c2, or it could be more than one frequency. Okay, it could be sine omega 1 bar t plus cos omega 2 bar t, something like that. Okay, but usually it essentially has a sinusoidal form. Okay, and that's why we are going to look at this particular form of f of t. Okay. Now, one thing that I want to note here straight away is that this omega bar is what is called as a forcing frequency. So that is the frequency at which you are applying the force. It is different from the natural frequency of the system. The natural frequency of the system, omega n, depends on the stiffness of the system and the mass of the system. Okay? Omega n is square root of k over m. And the damped natural frequency that we also learned about in the previous lectures is essentially omega n times square root of 1 minus zeta square, where zeta is a damping ratio. On the other hand, this omega bar is the forcing function. It is not a system parameter. It is a parameter of the force that you are applying. Okay, it is in some sense you control omega bar. Okay, omega n and omega d are essentially natural characteristics of the system, whereas omega bar is something that you control. Okay, now if you use f of t to be p naught sine omega bar t, then the governing differential equation becomes like that: mx double dot plus cx dot plus kx is p naught sine omega bar t. Okay. Now, when you have an equation like this, a differential equation like this, the solution contains two particular terms. One is what is called as the homogeneous solution, and the second is what is called as a particular solution. The homogeneous solution is nothing but the case where the right hand side is equal to 0. So mx double dot plus cx dot plus kx equal to 0. The solution to that is what is called as a homogeneous solution. Okay? And if you recall, the homogeneous solution is nothing but the free vibration solution, because that is what we were learning in the previous lectures. When f of t equal to 0, then that is the free vibration solution, and we have already derived this. We know what the free vibration solution is. Okay? In this particular case, this particular solution xp of t turns out to be something like this: g1 sine omega bar t plus g2 cos omega bar t. Okay. Now again, I want you to pay attention to the fact this omega bar is the forcing frequency. Okay, so the particular solution to this problem essentially depends on what frequency at which you are applying to the system. Okay, so what is the forcing frequency omega bar? Okay. The other thing that you want to notice is that this G1 and G2, these constants, will depend on omega bar. Okay, that is something that will be apparent when you go through the solution. But I want you to know that this G1 and G2 are not constants. This G1 and G2 will depend on omega bar itself. Okay, for a particular omega bar, G1 and G2 might be very small. For some other omega bar, G1 might be large, but G2 might be small, and vice versa, or both could be large. But G1 and G2 are essentially functions of omega bar, and they're also actually going to be functions of omega n, as we will see in a few minutes. Okay, so that is going to be a particular solution. So again, I want to recap this x of t, which is the total solution, is going to be composed of two parts: xh of t, which is the homogeneous solution, plus xp of t, which is the particular solution. Okay. Now, if you substitute this equation 2 into equation 1, okay, so that is the solution. Essentially, you're putting the solution back into the governing differential equation. What you're going to do is you are going to end up with essentially an equation like this. I have not put all these terms there because it's just tedious. But what I want you to understand is that every term in that equation, so essentially this is by putting the equation number 2 in equation number 1, you essentially get an equation where you have a bunch of sine omega bar t terms and a bunch of cos omega bar t terms. Okay? And the right hand side is the forcing function, which is p naught sine omega bar t terms. Okay? Now what you can do is you can combine all these sine omega bar t terms into one term and all cos omega bar t terms into another term, and write it as some a sine omega bar t is b cos omega bar t. Right? Again, if you are really interested, you can put all those things, do all the math, and then find out what a and b is. Okay? But that is not the purpose of this lecture. What I want you to understand is that you will essentially have two terms, sine omega bar t terms and cos omega bar t terms. Now, if you look at this equation, again, this equation is true for all time t. It doesn't matter whether t is 0, 0.1, or 3, or 5, or 1000, it doesn't matter. For all value of t, this such equation has to be satisfied. Okay? And the only way this equation can be satisfied for all time t is if both a and b are 0. That is the only way this equation can be satisfied. Okay? Now, you can essentially use this condition to find out G1 and G2. Okay, so just to go back, I told you that you are going to have a particular solution that has this G1 and G2, right? How do you find G1 and G2? Essentially using the fact that this A and B are equal to 0. Okay, again, you can do the math and confirm that G1 essentially has a form like this, okay, and G2 has a form like that. Okay, here if you look at it, there is a new term beta. Okay, what is this beta? This beta is omega bar divided by omega n. So essentially it is the ratio of the forcing frequency, the frequency at which you apply the force, divided by omega n, which is the natural frequency. Okay, so that is a beta. Okay, all the other terms are kind of familiar to you. This p naught is the amplitude of the force that you're applying. So if you think about it, f of t was p naught sine omega bar t. So that is the p naught. K is the spring constant. Beta, I just explained you what it is. And the zeta, of course, is the damping ratio, which is C over Cc. Okay? So that is your G1. And the G2 is also pretty similar. But you can see that looking at their form and function, it is going to be quite a bit of tedious math to get here. Okay? And I don't want to kind of go through that. Okay. Now, what you have done now is that we have found the particular solution, And that particular solution is, as we talked about, it is going to be G1 sine omega bar t plus G2 cos omega bar t. We have found G1 and G2 now. Okay, so we know what xp of t is. We already know what the homogeneous solution is. That is what we derived in the previous lectures, xh of t. So the total solution xp of t is going to be nothing but, the total solution x of t is going to be xp of t plus xh of t. Okay, so we know everything now. Okay, now one thing that you might recall is that the homogeneous solution, right, it decays over time. So if you recall, we plotted how xh of t evolves over time, and we saw that it is always going to keep going down, right? So this reduction is basically that e to the minus zeta omega n t. Okay, so what we know is that this xh of t, which is the homogeneous solution or the free vibration solution, it is essentially going to decay as a function of time, and it will essentially reach a value very close to zero for a finite amount of time, right? So if you wait enough time, this xh of t is not going to contribute at all. It essentially goes to zero. So the only thing that matters is xp of t, which is why it is called as the steady state solution. Okay, so if you wait for maybe a couple of seconds or maybe 10 seconds, right? After that, the only thing that contributes to your displacement is basically your particular solution, xp of t. Okay, so essentially you can say that x of t is nothing but xp of t. Okay, now we already looked at what x of t is, or xp of t is. We said xp of t is g1 sine omega bar t plus g2 cos omega bar t. Okay, now essentially using a small mathematical trick, you can write this g1 sine omega bar t plus g2 cos omega bar t as something a little bit simpler, and that is what I have done here. So you can write this x of t as just composed of a sine omega bar theta. Okay, again, this is something that you can try and derive yourself if you are interested, but x of t is going to look like that. Okay, now if you look at this x of t, there is something interesting here. Okay, the first term of this x of t is this p naught over k. Okay, so what is that p naught over k? That is essentially what is called as the stationary response of the system. So what I mean by that is that if you have a single degree of freedom system like this, okay, and then you apply just a constant force p naught, okay, then the displacement of the system is going to be p naught over k. Okay, so if you don't oscillate it, if you just apply a force and keep it, then the displacement of the system is going to be p naught over k. So that is the first term in the amplitude, okay, or the amplitude term of x of t, right? So that is somewhat interesting, right? And then you have another term that follows it, okay, which is 1 over square root of 1 minus beta square the whole square plus 2 zeta beta the whole square. Okay, so what is this term doing there? This term, if you look at it, is the term that depends on the frequency at which you are oscillating, because it depends on beta, and beta is nothing but omega bar over omega n. Okay, now you start to see how this solution is coming around. You have a p naught over k here, which is the amount of displacement the system will have if you just apply a constant force. And now if you take the same force amplitude but now oscillate it, your x of t is going to be quite different. And the amplitude of the vibration there could be quite a bit more. Okay, and of course you also have this time varying term sine omega bar t minus theta. Okay, so that is something that you must keep in mind. Okay, again, this is a lot of information here, but I just want you to focus on the big picture. Okay, the main thing is that the x of t, the displacement of a single degree of freedom system that is subjected to a force f of t, which is nothing but P naught sine omega over t in this particular case, is going to look like this. This part is the amplitude. Okay? How much is the system going to oscillate? Okay? What is going to be the maximum displacement? That is the amplitude, right? This part is the time varying part. Okay? And now you can take this amplitude part and then call it rho. And then you can kind of split that rho into two parts. One is the stationary response that I was just talking about, P naught over K. And this part is essentially the dynamic part, or dynamic amplification. And this theta is what is called as a phase angle. Okay, that is not so relevant or very relevant for our analysis, so I'm not going to talk about it too much. Okay, so essentially, if you think about what is x of t, it has an amplitude and a frequency of oscillation. The amplitude essentially comprises of two parts. One is the stationary response or the stationary amplitude, and a second term which is the dynamic amplitude or the dynamic amplification factor. Okay, now if you actually take this x of t and plot, okay, then it could be quite different from the x of t that you had for the free vibration system, or for that matter, a damped or an undamped case. Okay. Now, the main thing that we are interested, okay, as mechanical engineers, is this part here. Okay, this dynamic amplification part. Okay, because that is the one that is very crucial to our structures. Okay. Now we can start to see why by looking at. Before I do that, let me actually just give you an overall, version, and then we can look at it more carefully. Now, if you look at this particular term, 1 by square root of 1 minus beta square the whole square plus 2 zeta beta the whole square, think of a case where your beta is very close to 1 or actually equal to 1. Okay? Again, let me restate it. So, look at this term for the case beta equal to 1. So what does beta equal to 1 means? Beta is basically omega bar by omega n, which is basically the forcing frequency divided by the natural frequency. Now if beta is approximately equal to 1, this term here essentially goes to 0. Okay, because what's 1 minus beta square the whole square, that becomes 0. Right? So essentially the whole term becomes something like 1 by 2 zeta beta. Okay. Now I told you that the zeta is usually very much less than 1. Okay. Say zeta is 0.01 for example. Beta is 1. So this whole term is going to be nothing but 1 by 0.02, which is 50. Okay. Now what it's telling you is that if I just apply a force P naught, then I am going to only get a displacement of P naught over K. Okay, if I apply a constant force of P naught, I'll get a displacement of P naught over K. Now, if I take the same force, but if I don't actually keep it constant, but then oscillate this at a frequency that is close to the natural frequency of the system, then the amount of oscillation or the amount of displacement I'm going to get is going to be 50 times larger. Okay? Remember, you're applying the same force amplitude. You're not applying more force. You're applying the same force, but just that you're applying the force back and forth as a function of time. And now what you're seeing is that the displacement of the system is going to be 50 times larger. Okay? And if zeta is even smaller, it could be 100 times larger. Okay? This is very counterintuitive, because in one case you're applying a constant force. In this case, you're actually changing the direction of the force. Sometimes you're trying to put the force in the positive direction. Sometimes you're actually putting the force in the negative direction, because the force is P naught sine omega bar t. As t is varying, the direction of the force is changing. So instead of just applying force in one direction, you're essentially saying I'm going to apply force back and forth. Now you would think that in such a case that the amount of displacement will be lower, because you're not just pulling in one direction, you're in some sense like pulling and pushing at the same time, or pulling and pushing as a function of time. But what you see is that the amount of deflection this particular mass is going to have is sometimes 50 times this way, sometimes 50 times that way. Okay? And that is where the importance of vibration starts to sink in. Because you might think that if you apply this particular force, then I'm going to have only this much stress or this much displacement. But now if you start oscillating that force, then things can go really out of hand very quickly. Okay? And that's why when you look at actual mechanical systems that are rotating, systems that are translating, systems that have, torques being translated, motors being rotated, then the vibration aspect becomes as important as anything else. Okay? Now, you can take this rho, which is the amplitude of the vibration, and then plot it as a function of beta. Okay? And if you do that, you essentially will get curves like this. Okay? The second part that I talked about, this dynamic amplification factor, that is sometimes denoted by this symbol A. And if you plot this A as a function of your beta, you essentially get curves like this. Okay? And these are curves for different values of zeta. Okay? For the case where zeta is equal to 0, the damping ratio is 0, essentially you will get infinite displacement. Okay? I have not drawn it because it goes all the way up. It has no bounds. Okay? So what it's telling you is that if you have a single degree of freedom system that has 0 damping, zeta equal to 0, and then you start applying a force at a frequency that is close to the natural frequency of the system, essentially your displacements will explode. Okay? It will become close to infinite. Okay? Of course, it never happens in practice because things will break before they can displace, infinitely. Okay? But now, if you start add a little bit of damping, okay, if you have some element there that can dissipate energy, then things come under control. Okay? Now, if you go from zeta equal to 0 to zeta equal to 0.2, then the curve looks more like this. Of course, the amplification factor is still more than 1, but it's not infinite. It's maybe 10, it might be 5, right? Now, as you start increasing more and more, as zeta goes from 0 to 0.5 and 0.5 to 1 over square root of 2, at some point, essentially the amplitude you're going to get becomes less than 1. Okay? So again, I want to take a minute to explain what these curves mean. Okay? So we are looking at this dynamic amplification factor, A, which is the frequency dependent term of the amplitude. Okay? And we are plotting that as a function of beta, which is the forcing function divided by the natural frequency. Now, when beta equal to 0, it essentially means that you have a constant load. Okay? And in that case, the amplification factor is always 1, irrespective of what zeta is. But now, as you start increasing the frequency at which you are applying the force, then the amplitude usually increases. Okay? And then it essentially gets a maximum value close to beta equal to 1. It is not exactly equal to 1. It is actually close to equal to 1. And the actual number is given by 1 minus square root of 1 minus 1 by square root of 1 minus 2 zeta square. So zeta is usually small. So this beta value close to 1 is when you have the maximum amplification. Okay? But the amount of amplification depends on how much damping you have in the system. Okay? If you have a lot of damping, if zeta is large, then the amplification ratio becomes smaller, or the amplitude ratio becomes smaller. Okay? So again, this is kind of a very quick tour through the vibration of single degree of freedom system. But I hope that you got the main points, because we will be essentially using this particular system to analyze continuous systems in the lectures to come. Okay? With that, I will conclude this lecture, and I'll see you next time.